Good morning, everybody. This is Kankani, a system architect at Uber. It's great to be part of the community and talk about the memory efficiency problem using Uber use cases. The other contributors for this talk are not here today, so I'll be representing the team. So most of these efficiency problems that I'm going to talk about are a co-design effort between application, fleet management fabric, the capacity and hardware engineering. So would need a co-design effort across all of these and would like to join hands with the community to look at some of the problems that we can collaborate on. So to start with, talking about like the memory landscape from the highly performant L1 cache to the high density block-based NVMe flash devices. All of these memory tiers can be classified using different attributes like size, latency, read-write throughput, use cases, and cost. And as you see from right to left, the latency increases and the cost decreases. It is important to choose the right memory tier in order to realize some of the gains from the efficiency initiatives that we'll talk about in order to maintain the acceptable SLAs for the different application use cases. So let's take a look at some of the industry and Uber trends to begin with. Over the last 3 generations at Uber, we have almost tripled the core density from 48 cores to 128 cores. And the memory density and the bandwidth and cost has not changed in the proportion. So what we see is the dollar per gigabyte per month, the chart that you see, the cost is, memory cost has plateaued and is flattening. And hence it is becoming an increasingly higher percentage of the overall server cost. Across thousands of microservices that we deploy, we have seen an increase in the diversity of core to memory ratio across all of these microservices. And since we have a limited set of SKUs in our fleet, this breeds in a lot of inefficiency. And lastly, the physical limitations of the memory density and the number of channels on the next-gen servers means that it hinders the efficiency that we can unlock through code densification, which is part of our scale-up strategy. And it also means, like, as we are growing our fleet in terms of servers and cores, the number of DIMM counts increases, and with it, the power and cost increases as well. This has a lot of implications on our thermal and cooling solutions. So all in all, like, this is not a sustainable trend, and hence we need to double down on some of the memory efficiency efforts across our fleet. So before we go into the efficiency efforts, I would like to talk about a little bit about the overall overview of the Uber infrastructure landscape, platforms, and the commodities. Requests from a rider on an Uber app traverses a bunch of on-trip and post-trip components during the overall core trip flow. A series of microservices start responding to these requests, which is supported by our compute platform. As a part of that response, some of these microservices might want to read or write to the storage, for example, data streaming in Kafka. And then this data is pumped into our data warehouses, which is supported by our data platform. A bunch of analytics is being run in the background in the batch and real-time workloads. And this is fed into our AI/ML platforms for training and inference purposes. So net-net, we have about 4 SKUs that supports these different diverse sets of microservices. Across these different sets of hardware platforms, compute, storage, data, and ML, underlying hardware that is leveraged is different. Compute services, for example, runs high on memory, and data platform uses a lot of spinning disks. But net-net, end-to-end, if you see, the commodity cost across all of these platforms is dominated by memory. And in order to reduce the memory usage across these platforms, different layers of the stack need to be orchestrated in order to realize some of the gains and reduce the memory usage. For example, solutions need to be aware of what technologies are co-located in our containerized environment. Fleet management fabric like Kubernetes need to support near and far memory swapping using CXL. And while all of this is happening, we need to make sure the fleet health is managed and the service SLAs are being met. So this chart shows the diversity of P95 CPU utilization and P95 memory utilization across a diverse set of our microservices. As ideally, we would like all of these services to align on the solid blue line, but the dotted circles shows the opportunity for dynamic memory scaling, tiering, and pooling and disaggregation. So to solve for this, we have three main goals for SDM at Uber. The first one is we are focusing on reducing memory cost across all of the platforms. Secondly, we would like to enable memory expansion to support our scale-up strategy. The AIML workloads, for example, that have hyperparameter tuning and larger embedding tables require memory that goes beyond the DIMM channels that the next-gen servers can support. And we want to enable all of this and achieve this through a shared fabric-level orchestration, whether it's memory scaling, sizing, or tiering. We are not focusing on the memory bandwidth as a primary use case for now, but we may revisit that in later stages. So this is an overview of the memory efficiency initiatives that we have, and along the first column, the attributes that we have summarized it in terms of past, present, and what we're going to do in future. I'll walk through each one of this in detail in the next coming slides. So these are the results from right sizing of allocations based on our CPU scaling. As you can see on the chart on the right, there's a lot of over-provisioning of cores, the blue bars that you see, in the low CPU utilization area. And once we start right-sizing allocations based on CPU utilization metrics, we see a significant reduction in number of cores that gives us excellent savings in terms of number of host counts. As a next step to this, since the memory is becoming the higher part of the server cost, we would like to right-size allocations based on memory. Even if it results in stranding of cores, that would result in, we would be ahead in terms of TCO wins. And also, as we start looking at sizing these allocations based on memory utilization metrics, we want to find out other metrics as well for future memory scaling. Another way to unlock a significant efficiency saving is through multi-tenancy and colocation. This is done through our shared fabric, where a lot of services are grouped together in placement classes, and technologies are put into a single platform. A lot of benefit can be achieved by not managing buffers by each technology and actually grouping them and managing them in a centralized manner. So these two charts show the diversity in resources for our storage technologies, whether it is in terms of disks, memory, CPU, and so on. And even within each technology, the chart on the left shows the diversity in the core to memory ratio that we see across different storage instances. So now, as long as we are co-locating services based on single dimension like cores, the implication is that it can result into a lot of stranding of other resources like disk utilization, memory or disk capacity, and so on. Hence, what we need to do is look at multidimensional resource vectors that can look at like the total consumption, not only based on what the actual usage is for the service, but also based on what that service is preventing other services from using, what resources are being wasted because of that service. So these are some results from one of the use cases of co-locating two storage technologies together. When MySQL was enrolled in DocStore as co-located, we saw a reduction of 42% in hosts in one of the clusters. And after co-locating these storage technologies, we saw that the memory bottleneck takes over the CPU bottleneck, which is shown on the chart on the left. So hence it is important to collocate services based on memory to further improve the memory utilization rates that is becoming a bottleneck now. One other way to improve collocation is by making the shared storage fabric aware of different memory tiers. For example, there can be a lot of cost savings by collocating services that are tolerant to 1 or 2 NUMA hop latencies on a far memory with CXL, and that frees up the near memory for some of the high technology that requires low latency and free up the high cost memory tier. So this chart builds the case for memory tiering. On the y-axis, you see the ratio of hot to total memory usage for top 30 microservices sorted by their memory allocation. We use working set size as a proxy over a period of time for hot memory. The idea is that by moving cold pages to a lower memory tier in terms of its latency and cost, we can get significant cost savings. One observation we have was that 40% of the services showed memory coldness for at least 50% of the memory capacity. This is a huge opportunity. Even if we can overcommit 25% of the memory for 10% of the services, that can result in tens of millions of dollars in savings. So there are a few ways to accomplish memory tiering. One of the ways is using ZSwap feature, which is available in Linux kernel 3.11 onwards. So the ZSwap feature works as a swap device to avoid machines running out of memory. But instead, we can take a proactive approach of compressing cold pages in memory using ZSwap. With the availability of high bandwidth cache coherent new CXL interface, we can retire cold pages to CXL devices through kernel managed auto tiering and some of the other page placement algorithms. And we are also engaging with different CXL vendors to benchmark the 1 NUMA hop latency delay and its implication on application performance degradation. For example, for one of the Redis benchmarks, by moving 10% of the accesses to CXL far memory device, we saw 5 to 10% performance degradation. So there's more work to be done there. And last but not the least is the pooling initiative. This one is a bit far in future, 3+ years perhaps, but we see this as the next logical step after direct attached CXL devices. There's a lot of software error handling flows, kernel update management, out-of-band management that needs to happen before we can unlock full potential of this solution. So the chart on the top, the bar chart on the top shows the memory allocation, and you can see that a lot of memory buffers and low latency host agents can be pooled, and that memory can be reduced by pooling into a appliance. And a chart at the bottom right shows the memory profiling for different services by their business criticality and in terms of their performance and latency. So one of the things we can do is, for example, targeting tiers like 3 and 5 that show memory coldness and low in terms of business criticality, and pilot those kind of services for the pooling solution to begin with. So with those memory initiatives, I would like to highlight a few challenges that we faced. Our data centers are divided in zones and regions, and we over-provision memory to tolerate regional and zonal failovers. So while scaling the memory allocations, it is hard to predictably estimate the memory requirements during these failover scenarios using the utilization metrics similar to what we use for CPU. Another challenge we face is out-of-memory errors and the resulting reliability impact on our services due to that. And we found it's mostly because of our suboptimal reclamation algorithms, and we hope with the future Linux upgrades and the better reclamation algorithms available, this will improve. As we are introducing new servers into our fleet, the heterogeneity of SKUs in our fleet is increasing, and that is posing another challenge in terms of like resource stranding, and we are looking at resource vectors to reduce this waste. Orchestration of swap from near to far memory using CXL and its implications on application performance degradation, especially in a multi-tenant environment, poses another challenge. For example, what we are seeing is we are sometimes limited by the worst case service to determine how much memory we can offload in a multi-tenant environment. So with that, to wrap up my talk, I have a few call to actions. Collaboration and hardware software design across applications, kernel capacity, hardware engineering will be needed to realize some of these gains. Industry partnerships will be required for memory tiering with CXL, whether it is leveraging kernel page promotion techniques or leveraging open source work like PSI and C Group V2s. We look forward to working with the community and determine like what kind of memory we can offload. And standardization is needed across CXL vendors for getting common feature sets, for example, RAS features, fault detection and diagnosis, in order to get to a common interface. OCP specification for memory expansion with CXL would be very useful. So looking forward to that. So all in all, I feel like we have just begun to scratch the surface, and there's a lot of exciting work ahead for Uber in this domain, and looking forward to learning and joining hands with the community here and working on the common problem sets to solve this problem. With that, that's all I have. Thank you for patiently listening, and looking forward to chatting with you guys. Thank you.